The universe is expanding faster than it should be. Not slightly faster, not within the margin of error. Faster by a number that has resisted every attempt to explain it for over a decade, that has survived every upgrade to the instruments measuring it, but has gotten worse as the measurements have gotten better. Two independent methods of measuring the expansion rate of the universe disagree with each other by roughly 10%. In a field where a 1% discrepancy is cause for serious investigation, 10% is not a rounding error. It is not a calibration problem. It is not human mistake. At this point, after this many checks, most physicists believe it is telling us something real about the universe. Something that our best theory of cosmology, a theory that correctly predicted the existence and temperature of the cosmic microwave background, that accurately describes the formation of galaxies, that has been confirmed by thousands of independent observations across decades, does not account for. If you enjoy videos that follow scientific controversies, where the official answer is, "We don't know yet," and the unofficial answer is, "This might break everything," I'd genuinely appreciate it if you hit that like button and subscribe. It helps more than you know. Now, settle in, get yourself nice and comfortable. Let's begin. Here is what most people think the situation is. Scientists measured how fast the universe is expanding, got a number, and everyone agreed. The number is called the Hubble constant, named after Edwin Hubble, who first measured the recession of galaxies in 1929, and it describes how fast the universe expands per unit of distance. Specifically, it tells you how many kilometers per second a galaxy recedes for every megaparsec of distance between you and it. 1 megaparsec is about 3.26 million light years. The commonly cited value is around 70 kilometers per second per megaparsec, give or take. Scientists measured it, agreed, moved on. That is what most people think. That is not what happened. What actually happened is this. Two separate groups of scientists, using two fundamentally different methods, both measured the Hubble constant with precision that was supposed to settle the question, and they got different answers. Not slightly different, different by an amount large enough that both answers cannot simultaneously be correct, if our current understanding of the universe is right. One group measured it from the early universe, from the cosmic microwave background, the relic radiation from 380,000 years after the Big Bang, and got approximately 67.4 kilometers per second per megaparsec. The other group measured it from the local universe, from a chain of distance measurements reaching out through the nearby cosmos, and got approximately 73 kilometers per second per megaparsec. The gap between these two numbers is called the Hubble Tension, and it is the most serious unsolved problem in observational cosmology today. 73 versus 67.4. That gap sounds small. It is not small. The uncertainty on each measurement has been refined to the point where, statistically speaking, the probability that both measurements are correct under the same cosmological model is less than 1 in 100,000. In physics, a 1 in a million probability is called a 5 sigma result and is the standard for claiming a discovery. The Hubble tension is not quite at 5 sigma. It sits around 4 to 5 sigma, depending on the specific measurements and analysis methods, but it is deep in the territory where coincidence or measurement error stop being reasonable explanations. The instruments have been checked, the methods have been checked, the teams have checked each other's work. The tension remains. To understand why this matters as much as it does, why this is not just an abstract disagreement between two numbers, but a potential crack in the foundation of modern cosmology, you need to understand what the Hubble constant actually is, and what it would mean for the two measurements, to genuinely disagree. The Hubble constant is not just a description of how fast the universe is expanding right now. It is a parameter embedded in the standard model of cosmology, a model called lambda-CDM, where lambda stands for the cosmological constant, the mathematical term for dark energy, and CDM stands for cold dark matter. Lambda-CDM is the framework within which essentially all modern cosmological observations are interpreted. It has 6 free parameters, 6 numbers that must be measured rather than derived from first principles, and the Hubble constant is one of them. The other 5 include the density of ordinary matter, the density of dark matter, the amplitude and tilt of the initial density fluctuations, and the optical depth of the universe to reionization. These 6 numbers, plugged into the equations of general relativity and the standard model of particle physics, produce predictions that match observations with extraordinary precision across an enormous range of scales and epochs. To appreciate what extraordinary precision means in this context, consider what lambda-CDM has gotten right. It predicted the existence and temperature of the cosmic microwave background before it was measured precisely. The prediction matched observations to better than 1%. It predicted the ratio of hydrogen to helium produced in the first 3 minutes after the Big Bang, a ratio measured in the oldest, least chemically processed stars in our galaxy. And the prediction matched the observation to within observational uncertainties. It predicted the large-scale distribution of galaxies, the way galaxies cluster together in filaments and walls and voids, with characteristic statistical properties on specific scales, and surveys have confirmed these predictions across hundreds of millions of light-years. It predicted the existence of baryon acoustic oscillations, a preferred scale in the galaxy distribution imprinted by sound waves in the early universe, and these have been measured in multiple galaxy surveys with the predicted amplitude and at the predicted scale. Lambda-CDM is not a rough sketch. It is a precision theory that has passed dozens of independent tests across decades of observations. This makes the Hubble tension more serious, not less. When a theory that works this well, in this many contexts, makes a prediction that disagrees with a direct measurement by 5 sigma, the disagreement cannot be brushed aside. Either the measurement is wrong, which becomes harder to maintain with each passing year of continued confirmation, or the theory is missing something. Both possibilities have been taken seriously. Neither has been definitively resolved. The history of how the tension was discovered is worth understanding, because it illustrates how a fundamental problem in cosmology can develop gradually over years through the accumulation of increasingly precise measurements. The story begins before Hubble. In the early 20th century, the prevailing view was a static universe, one that had existed forever, neither expanding nor contracting, held in equilibrium by some mechanism not yet specified. Einstein himself, when he first applied his general relativity equations to the universe as a whole in 1917, found that the equations did not naturally produce a static universe. Gravity would cause any matter-filled universe to collapse unless something prevented it. He introduced the cosmological constant, a term in the equations representing a repulsive energy of empty space, to balance gravity and produce a static solution. He considered this his greatest blunder after expansion was confirmed. The observational case for expansion built slowly through the 1920s. Vesto Slipher at Lowell Observatory began measuring the spectra of spiral nebulae in 1912 and found that most showed redshifts. Their spectral lines were shifted toward longer, redder wavelengths, indicating recession. By 1925, Slipher had measured recession velocities for 45 spiral nebulae, with most receding at hundreds of kilometers per second. No one quite knew what to make of this. The nature of the spiral nebulae themselves, whether they were nearby gas clouds or distant island universes, was still contested. Hubble settled the distance question with his Cepheid observations in the mid-1920s, establishing that the Andromeda Nebula and others were separate galaxies millions of light years away. Then, in 1929, he combined his distance measurements with Slipher's recession velocities and published the correlation: recession velocity proportional to distance. This was not the definitive discovery of the expanding universe. Hubble's sample was small, his distances had significant uncertainties, and the data had scatter that a skeptic could dismiss. But it was the first clear evidence, and it came with a value of what would later be called the Hubble constant, approximately 500 kilometers per second per megaparsec. That value was wrong by a factor of 7 because the Cepheid period luminosity relation Hubble was using was systematically miscalibrated. The calibration errors were not identified until the 1950s, when Walter Bade realized that there were two distinct populations of Cepheids with different period luminosity relations, and that Hubble had been applying the wrong relation to the wrong population. Correcting the error dropped the Hubble constant from 500 to roughly 100 kilometers per second per megaparsec. From 100, the next 4 decades were slow and contentious convergence. Alan Sandage, Hubble's successor at the Carnegie Observatories, argued for a low value around 50. Gerard de Vaucoulot argued for a high value around 100. The two camps were separated by a factor of 2, and the disagreement was driven by real, systematic differences in their distance measurement methods and calibrations. The debate was professional and sometimes personal. The astronomy community of the mid-20th century was small enough that the principal investigators knew each other well and had strong opinions about each other's work. While the first one, the factor of 2 uncertainty in the Hubble constant, persisted for decades, a standing embarrassment for a field that prided itself on precision. The Hubble Space Telescope was sold to NASA in part on the promise of resolving this factor of 2. The telescope's sharp resolution, operating above the blowing effects of Earth's atmosphere, would allow Cepheids to be measured in galaxies far enough away to be in the pure Hubble flow, avoiding the contamination from local peculiar motions that had plagued ground-based measurements. Wendy Friedman led the key project team that executed this program through the 1990s, and the 2001 final result, 72 plus or minus 8, did resolve the factor of 2 debate. The Hubble constant was in the 70s, not the 50s or the 100s. Sandage and de Vaucoulot had both been approximately half right. At the same time that the key project was running, a revolution was happening in cosmology from a completely different direction. In the late 1990s, 2 teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova team, led by Brian Schmidt and Adam Rees, By using Type 1a supernovae to measure not just the current expansion rate, but the history of the expansion, whether the expansion was slowing down due to gravity or doing something else. The expectation was deceleration. What they found was acceleration. The universe was expanding faster now than it did in the past. Dark energy, whatever is driving the acceleration, was discovered in 1998, and the discoverers won the Nobel Prize in 2011. The cosmological constant Einstein had introduced and abandoned was rehabilitated. Lambda CDM became the standard model. The CMB measurements that followed through the 2,150 years, WMA, then Planck, established lambda CDM with 6 precisely measured parameters. The Hubble constant inferred from these measurements was consistently around 67 to 68. Meanwhile, the SH0ES team was using the refurbished Hubble Space Telescope to push the distance ladder to higher precision, finding Hubble constants consistently around 73 to 74. The tension latent in the data since at least the Planck 2013 results was acknowledged but not yet alarming. It seemed plausible that some combination of systematic errors in both measurements was responsible. Year by year through the 2010s, the systematic error budget in both measurements shrank. The tension did not shrink, it grew. The 2016 SH0ES result made it 3.4 sigma. The 2019 result made it 4.4 sigma. The 2022 result, incorporating JWT confirmation and the full HSTC Sepia dataset, established it at approximately 5 sigma. By this point, the field had accepted that the tension was real. The question was no longer whether to take it seriously. The question was what it meant. The story of the Hubble tension is also the story of a community learning to disagree productively. The principal investigators, Rees on the distance ladder side, Planck team members on the CMB side, have been unfailingly honest about the uncertainty in their own measurements and genuinely open to the possibility that their teams made mistakes. The cross-checks have been extensive and transparent. The James Webb Space Telescope CFARD measurements were proposed precisely to test a specific systematic concern about the SH0ES CFARDs, and the SH0ES team supported that test, knowing it might reveal an error in their own work. It did not. The scientific process, at its best, is exactly this: precise measurement, honest reporting, rigorous cross-checking, and following the data wherever it leads, including into uncomfortable places where the standard model does not adequately explain what is observed. The uncomfortable place the Hubble tension has led is a confrontation with lambda CDM that has no clear resolution. Every attempt to modify the model to resolve the tension has created problems elsewhere. Every systematic error hunt has come up empty. The tension persists, sharpens, and demands explanation. This is science at the frontier, not the tidy narrative of a solved problem, but the messy, ongoing process of a real discrepancy being worked through by a community that does not yet know the answer. What we know with confidence: the universe is expanding at 67.4 kilometers per second per megaparsec, according to the early universe, and at 73.04 kilometers per second per megaparsec, according to direct local measurement. The two numbers are inconsistent at the 5 sigma level. Neither measurement has a confirmed systematic error large enough to account for the discrepancy. The standard cosmological model, which has been confirmed by dozens of independent observations, does not predict both numbers simultaneously. Something is missing from the model, or something is wrong with one of the measurements at a level that has not been identified. What we do not know which of the many proposed explanations, if any of the currently proposed ones, is correct. Whether the resolution will require a small modification to land a CDM or a fundamental rethinking. Whether the tension is connected to other anomalies in the cosmological data, like the S8 tension, or whether it stands alone. How long it will take to resolve. What is coming, instruments and experiments with the precision to discriminate between the proposed solutions. The Simons Observatory, DESI Year 3 and Year 5, the Vera Rubin Observatory, Euclid, the Nancy Grace Roman Space Telescope, Advanced LIGO, and eventually the Einstein Telescope. Each of these will add constraints that either rule out proposed solutions or support them. The resolution will come through data, not through theoretical creativity alone. The universe has already encoded the answer. The instruments being built and operated right now are learning to read it. 73 versus 67.4. The story begins, in a real sense, with the original Hubble Space Telescope. Key Project, a program led by Wendy Friedman and her collaborators that ran through the 1990s and published its final results in 2001. The Key Project's goal was to measure the Hubble constant to 10% precision, the key referring to one of the primary scientific justifications for building the Hubble Space Telescope in the first place. The team used the telescope's sharp resolution to identify and measure Cepheid variable stars in 31 galaxies, calibrating the distance ladder and reaching a final answer of 72 plus or minus 8 kilometers per second per megaparsec. The uncertainty was symmetric and large enough to encompass a wide range of possible values. The tension with CMB-based measurements, which were not yet at the precision level they would later reach, was not apparent. The Key Project result was celebrated as a major achievement. The Hubble constant question seemed, provisionally, answered. The situation changed in 2013 when the Planck satellite published its first full-sky CMB analysis. The Planck team derived a Hubble constant of 67.3 kilometers per second per megaparsec, with an uncertainty of about 1.2. This was the most precise CMB-based Hubble constant measurement ever made, and it was significantly below the Key Project's central value of 72. The Planck team noted the discrepancy with local measurements, but treated it cautiously. The local measurements at the time still had enough uncertainty that the disagreement was not statistically alarming. The tension sharpened with subsequent work by the SH0ES team. In 2016, Adam Rees and collaborators published a Hubble constant measurement of 73.24 plus or minus 1.74, using improved Cepheid data from the Hubble Space Telescope. The time is a scandal. The discrepancy with Planck had grown to 3.4 sigma. In 2019, the SH0ES team published 74.03 plus or minus 1.42. The discrepancy with Planck had grown to 4.4 sigma. In 2022, using the full Hubble Space Telescope dataset, optimized for Cepheid measurements, they published 73.04 plus or minus 1.04, and the discrepancy with the Planck value was approximately 5 sigma. With each successive measurement, as both the CMB and distance ladder analyses got more precise, the tension grew rather than shrinking. This is the opposite of what you expect from a measurement error. Errors do not systematically sharpen into crises as the measurements get better. Real discrepancies do. The Planck collaboration published its final data release in 2018 with a Hubble constant of 67.4 plus or minus 0.5. This remains the most precise CMB-based measurement. The SH0E result of 73.04 plus or minus 1.04 remains the most precise distance ladder measurement. The two numbers are separated by 5.64 kilometers per second per megaparsec. The combined uncertainty accounting for both measurements' error bars places this discrepancy at approximately 5 sigma, 1 in 3.5 million chance of occurring by statistical accident if both measurements are correct under the same model. Now, let's talk about the distance ladder in more detail, because it is the heart of the local measurement and the place where most systematic error hunting has focused. The cosmic distance ladder is a sequential chain of measurement techniques, each calibrated against the one below it and reaching further into the universe than the one below it. The logic is that no single technique works across the entire range of distances relevant to cosmology, from the nearby solar neighborhood to galaxies billions of light years away. So you build a chain. Each rung reaches further and is calibrated by the rung beneath it. The calibration propagates errors. An error on the first rung affects all subsequent rungs, multiplied by whatever factor the subsequent rungs magnify it. The first rung is geometric parallax. When Earth moves from one side of its orbit to the other over 6 months, nearby stars appear to shift against the background of more distant stars. The angular size of this shift, the parallax angle, is inversely proportional to the star's distance. No assumptions about physics are required. The measurement is geometry. The distance to a star with a parallax angle of 1 arcsecond is defined as 1 parsec, 3.26 light years. The Gaia satellite, in its ongoing mission that began in 2013, has measured parallaxes to over 1 billion stars with micro-arcsecond precision. These measurements anchor the bottom of the distance ladder with geometric certainty. A micro-arcsecond is 1 millionth of 1 arcsecond, the angle subtended by a human hair viewed from 10,000 kilometers away. The second rung is Cepheid variable stars. Cepheids are a class of supergiant stars that pulsate in brightness, with periods ranging from about 1 day to 100 days. In 1908, Henrietta Swan Leavitt, working at the Harvard College Observatory, discovered that the Cepheids in the Small Magellanic Cloud, a satellite galaxy of the Milky Way, showed a clear relationship between their pulsation period and their luminosity. Longer period Cepheids were intrinsically brighter. This period luminosity relation, now called a Leavitt law, turned Cepheids into standard candles. Measure the period, infer the luminosity, compare to apparent brightness, calculate the distance. Leavitt's discovery enabled the measurement of distances across millions of light years. It was the foundation for Hubble's determination that the Andromeda Galaxy was a separate island universe and not a nebula within the Milky Way. It has been the backbone of extragalactic distance measurement for over a century. The calibration of the Cepheid period luminosity relation requires knowing the distances to Cepheids through geometric methods, parallax. Before Gaia, this was done using a handful of Cepheids close enough to have measurable Hipparcos satellite parallaxes, supplemented by the distance to the Large Magellanic Cloud, measured through geometric methods, including eclipsing binary stars. Gaia dramatically improved this calibration by measuring parallaxes to thousands of Milky Way Cepheids with micro-arcosecond precision. The SH0ES team used Gaia Data Release 3 parallaxes in their 2022 analysis, incorporating over 1,000 Milky Way Cepheids as calibrators. The calibration is now the most precise it has ever been, and the Hubble constant derived from this calibration is still 73. The third rung is Type A supernovae. A Type A supernova is a thermonuclear explosion of a white dwarf star, the dense remnant of a sun-like star that has exhausted its nuclear fuel, that occurs when the white dwarf accretes enough mass from a companion to exceed the Chandrasekhar limit, the maximum mass a white dwarf can support, at which point electron degeneracy pressure fails and the star explodes. Because the triggering mechanism is always the same, the Chandrasekhar limit, Type A supernovae have remarkably consistent peak luminosities. They are not perfectly standard candles. The peak luminosity varies somewhat with the shape of the light curve, the rise and fall of brightness over days to weeks. But this variation is correlated with the light curve shape in a systematic way discovered by Mark Phillips in 1993. Brighter supernovae decline more slowly, and correcting for this correlation makes Type 1a supernovae into standardizable candles, good to about 10% in distance. Type 1a supernovae reach peak brightness comparable to the entire host galaxy, making them visible across billions of light years with current telescopes. This is what makes them so valuable. They extend the distance ladder from the tens of millions of light years reachable with Cepheids to the billions of light years with a Hubble flow, the pure expansion of space, free of local gravitational motions, dominates the recession velocities. In this regime, measuring recession velocity and distance gives the Hubble constant directly, without contamination from the random motions of galaxies within clusters and WOOPs. The SH0ES team used 42 Type 1a supernovae in galaxies whose distances were calibrated with Cepheids, and 277 supernovae at higher redshifts to establish the absolute calibration of the supernovae and then measure the Hubble constant. Every step of this analysis was performed with checks against potential systematic errors. The result? 73.04 kilometers per second per megaparsec. This number has now been confirmed, independently and with different methods, by multiple teams. The H0 Likau gravitational lensing result, the Megamaser cosmology project water maser result, the surface brightness fluctuation result from Blakesley and collaborators. They all get values in the range 72 to 75. They use completely different physical phenomena to measure distances. They have completely different systematic errors, and they all agree with each other, disagreeing instead with the CMB. The pattern is clear, and it has one straightforward interpretation. The local universe is expanding faster than Lambda CDM predicts, based on the early universe. The question is why? One possibility that deserves more attention than it typically gets in public discussions is that the tension is telling us something about the nature of dark energy, specifically in the recent past, the last few billion years of cosmic expansion. The current epoch of accelerated expansion began about 5 billion years ago, when dark energy became the dominant component of the universe's energy budget. Before that, the universe was decelerating. Gravity was slowing the expansion. The transition from deceleration to acceleration is encoded in the expansion history, and small changes in that transition could shift the effective Hubble constant measured from supernovae in specific redshift ranges. The dark energy equation of state parameter, W, describes the relationship between dark energy's pressure and its energy density. The cosmological constant has W exactly equal to -1. This is a fixed, defining property of vacuum energy. If dark energy is a dynamical field, quintessence, W can differ from -1 and can evolve over time. A common parametrization used in the field is WA equals W0 plus WA1 minus A, where A is the scale factor of the universe, equal to 1 today and less than 1 in the past. Different values of W0 and WA correspond to different histories of dark energy. The Desi-Baryon-Oscarsic oscillation results, published in 2024, found hints that the data prefers W0 slightly greater than -1 and WA significantly negative, meaning dark energy was weaker in the past and is approaching the cosmological cell. Constant value today, or possibly crossing through it, phantom crossing. This is a specific, unusual behaviour that most quintense models do not produce naturally. It requires either a model with specific features or a more exotic dark energy sector. The statistical significance is not high enough to claim a detection, but it is high enough to be inconsistent with the simple cosmological constant at about the 2.5 sigma level when multiple datasets are combined. If this hint is confirmed by DESI Year 3 data, it would not directly resolve the Hubble tension. The specific behaviour suggested does not obviously push the CMB-derived Hubble constant upward, but it would firmly establish that Lambda CDM is not the final description of dark energy, opening the theoretical space for modifications that might resolve tension. And it would represent the beginning of a new era in cosmology, the era of characterizing dark energy rather than simply detecting it. There is one more proposal worth discussing, one that is more conservative than modifications to new physics, but more radical than systematic errors. Some researchers have argued that the problem is not in the physics, but in the statistics. Specifically, that the standard way of combining cosmological datasets and quoting tensions does not correctly account for the prior assumptions built into each analysis, and that a more careful Bayesian treatment would reveal the tension to be less severe than the headline sigma numbers suggest. This is not a popular view among specialists who have studied the tension in detail, but it is not a fringe view either. The argument is that the Planck CMB analysis makes specific assumptions about the shape of the CMB power spectrum at very small angular scales, scales near the resolution limit of the satellite, and that these assumptions influence the inferred Hubble constant at the sub-percent level. Similarly, the distance ladder analysis makes specific assumptions about the calibration of the Cepheid period luminosity relation and about the treatment of outliers in the supernova sample. A different set of reasonable assumptions, the argument goes, might produce results that are in better agreement. The rebuttal is that all reasonable variations on the assumptions have been tried and the tension persists. The truth is that no one can currently say with certainty what the resolution of the Hubble tension will be. The field is in the middle of a genuine scientific controversy, being driven toward resolution by a generation of instruments and experiments whose results will accumulate over the next decade. The Simons Observatory will constrain early dark energy. DESI Year 3 and 5 will characterize the dark energy equation of state. Euclid and Roman will measure weak lensing and barium acoustic oscillations across wide areas of sky. Advanced LIGO and, eventually, the Einstein telescope will accumulate standard siren measurements. The Vera Rubin Observatory will discover tens of thousands of supernovae. The James Webb Space Telescope will continue to improve distance measurements in nearby galaxies. All of these instruments are, in a sense, aimed at the gap between 67.4 and 73. They are the tools humanity is using to answer the question the universe is asking. The question is fundamental. Is the standard model of cosmology complete? Or is it pointing, in the specific number of the Hubble constant, toward physics it does not yet contain? The history of cosmology suggests the latter. The universe has consistently surprised us. The expansion was discovered by Hubble in 1929, when the prevailing assumption was a static cosmos. The acceleration of that expansion was discovered in 1998 by Rees and Perlmutter and Schmidt, requiring the introduction of dark energy into the model. The precise flatness and uniformity of the universe required the introduction of inflation. Every time cosmology has encountered a genuine tension between prediction and measurement, the resolution has involved new physics, not a measurement error, not a statistical artifact, but a real feature of the universe that the previous model had missed. The Hubble tension may be the next entry in that sequence. It may require adding a new parameter, early dark energy, extra neutrino species, and modified gravity term, to a model that has already absorbed dark energy and dark matter and inflation without breaking. Or it may require something more fundamental, a rethinking of the assumptions that underlie Lambda CDM, from the cosmological principle to the nature of dark matter to the behavior of gravity on cosmological scales. Two numbers, 67.4 and 73, a gap of 5.6 kilometers per second per megaparsec. The universe is expanding faster than the model says it should. After a decade of checking, the model is not wrong enough to discard and not right enough to trust completely. That is where we are. That is what the next decade of astronomy is aimed at resolving. And when the resolution comes, through the accumulation of gravitational wave events, or the Simons Observatory's early dark energy measurement, or Desi's dark energy equation of state, or some combination of all of them, it will be one of the most significant moments in the history of cosmology since Hubble first pointed his telescope at the Andromeda Nebula and realized it was not a nebula at all. When you measure the Hubble constant from the cosmic microwave background, you are not directly measuring the current expansion rate. The CMB is a snapshot of the universe at 380,000 years old, when it was a completely different place, a hot, dense plasma transitioning into a transparent gas as the first atoms formed. The expansion rate at that epoch was very different from today. What you measure from the CMB is a set of parameters describing the early universe, and then you use lambda CDM to calculate what those parameters imply for the current expansion rate. The CMB-derived value of 67.4 is not a direct measurement of today's universe. It is a prediction based on early universe data and the assumption that lambda CDM correctly describes the universe's evolution from then to now. When you measure the Hubble constant from the local universe, from the distance ladder, you are making a direct measurement of today's expansion rate. You are measuring how fast nearby galaxies are moving away from us and at what distances, and computing the ratio. No model is required, in principle. The measurement is empirical, grounded in observable reality right now. The local value of 73 is not a prediction. It is a measurement. The tension between these two numbers is therefore a tension between a prediction and a measurement. Lambda CDM, calibrated on early universe data, predicts a current expansion rate of 67.4. Direct measurement of the current expansion rate gives 73. If both numbers are right, the CMB analysis is correct and the local distance ladder is correct, then lambda-CDM is wrong. Not slightly wrong. Wrong in a way that requires either a modification of the model or the addition of new physics that the model does not currently contain. This is a big claim. Let's make sure you understand exactly how confident we should be in each measurement, and why neither one is easy to dismiss. The CMB measurement comes primarily from the Planck satellite, a European Space Agency mission that observed the cosmic microwave background from 2009 to 2013, with the most precise instruments ever built for the purpose. The Planck team measured the temperature fluctuations in the CMB across the entire sky with angular resolution of about 5 arc minutes and temperature sensitivity of a few microkelvin, millionths of a degree. From these fluctuations, they extracted the 6 lambda-CDM parameters with percent-level precision. The Hubble constant they derived, 67.4 kilometers per second per megaparsec, came with an uncertainty of about 0.5 kilometers per second per megaparsec. This is a measurement precise to less than 1%. The Planck result was not the only CMB-based measurement. The Atacama Cosmology Telescope, a ground-based instrument in Chile, published an independent CMB analysis in 2020 that gave 67.6, consistent with Planck to within the uncertainties. The South Pole Telescope gave similar results. Every CMB-based measurement of the Hubble constant that has been published from every instrument has come in around 67 to 68. The early universe measurements are internally consistent. They all agree with each other. The local measurement comes primarily from a program called the Hubble Space Telescope Key Project, which was succeeded by the SH0 team, supernovae H0 for the equation of state, led by Adam Rees at Johns Hopkins University. Rees shared the 2011 Nobel Prize in Physics for the discovery of the accelerating expansion of the universe, and he has spent the subsequent decade refining the local measurement of the Hubble constant with increasing precision. The SH0 approach uses what is called the cosmic distance ladder, a chain of overlapping distance measurement techniques that together allow astronomers to measure distances across billions of light years with calibrated accuracy. The first rung of the ladder is parallax, the apparent shift in position of nearby stars as Earth moves around the Sun, which allows direct geometric measurement of distances to stars within a few thousand light years. No assumptions required. Basic trigonometry. The second rung uses Cepheid variable stars, stars that pulsate with periods precisely linked to their intrinsic brightness, allowing their distances to be inferred by comparing apparent brightness to intrinsic bright 1, alien force by 9.2. Cepheids can be measured in galaxies up to about 40 million light-years away. The third rung uses Type A supernovae, stellar explosions of remarkably consistent intrinsic brightness, visible across billions of light-years, calibrated by Cepheids in nearby galaxies. From the supernovae, you can measure distances to galaxies far enough away that their recession velocities are dominated by the Hubble flow, the pure expansion of space, rather than local gravitational motions. From those distances and recession velocities, you compute the Hubble constant directly. The SH0 team's most recent results, published in 2022, using data from the Hubble Space Telescope, gave 73.04 kilometers per second per megaparsec with an uncertainty of 1.04. This was the most precise local measurement ever made at the time of publication. The James Webb Space Telescope subsequently observed Cepheids in nearby galaxies as a cross-check, and its results, published in 2023 and 2024, confirmed the Cepheid distances measured by Hubble. The Webb observations actually tightened a constraint, confirming that the Cepheids themselves were not the source of the discrepancy. The local value is 73. The uncertainty on that 73 is about 1%. The CMB value is 67.4. The uncertainty on that 67.4 is about 0.7%. They do not overlap. The first response of any good scientist to a discrepancy like this is to look for systematic errors, mistakes in the measurement that are not captured by the quoted uncertainties. Systematic errors are different from random errors. A random error is statistical noise that averages out with more data. A systematic error is a consistent bias, something wrong with the method, the instrument, or the analysis that pushes the result in one direction. Systematic errors are the reason that precise measurements are hard, and they are the first thing to look for when two precise measurements disagree. The SH0ES team has been hunting for systematic errors in their distance ladder for over a decade. Their approach is methodical and public. They publish every analysis step, every dataset, every assumption, specifically so that other researchers can attempt to find the error. The scrutiny has been intense. The Cepheid measurements, the second rung of the ladder, have received the most attention because they are the crucial link between the nearby geometric measurements and the distant supernova measurements. Crowding is one of the most discussed potential systematics. Cepheids used to calibrate the distance ladder are in nearby well-resolved galaxies, while Cepheids used in the measurement step are in more distant galaxies where the angular resolution is worse. In the more distant galaxies, stars that are too close together to be individually resolved by the telescope are blended into single brighter sources. If a Cepheid is blended with a neighbour, it appears brighter than it actually is, causing its distance to be underestimated. Systematic underestimation of distances would systematically overestimate the Hubble constant. This is a real effect. It exists, and the SH0ES team applies crowding corrections derived from artificial star tests, where fake stars of known brightness are injected into the images and recovered to calibrate the bias. After the crowding corrections, the tension remained. The James Webb Space Telescope then provided the most direct test of crowding as an explanation. JWST observes in infrared wavelengths, where its diffraction-limited resolution, the fundamental limit set by the wave nature of light, is comparable to or better than the Hubble Space Telescope at optical wavelengths for nearby galaxies. But its superior sensitivity and stability allow it to measure Cepheids in these galaxies without the resolution limits that affect Hubble in more distant galaxies. The JWST measured Cepheids in 7 galaxies that anchor the supernova calibration, the same galaxies used by SH2Es, and found distances consistent with the Hubble Space Telescope measurements to within the statistical uncertainties. Crowding was not systematically biasing the SH0ES distances. Dust is another candidate. Interstellar dust absorbs and scatters starlight, making stars appear fainter and redder than they actually are. If dust in the Cepheid host galaxies is making the Cepheids appear fainter than their true brightness, the inferred distances would be overestimated and the Hubble constant would be overestimated. The SH0ES team addresses dust by observing Cepheids in multiple optical and infrared bands. Because dust affects different wavelengths differently, it absorbs blue light more than red light, more red light than infrared. Measuring the colour of a Cepheid tells you how much dust is in front of it, and the measurement in infrared wavelengths is much less sensitive to dust than optical measurements. The JWST infrared measurements again confirmed the Hubble Space Telescope distances, arguing against dust as a systematic. Metallicity, the abundance of elements heavier than hydrogen and helium in the Cepheid host stars, affects the period luminosity relation at a level of a few percent per unit of metallicity difference. Cepheids in the calibration galaxies and Cepheids in the measurement galaxies have different typical metallicities, and if the metallicity correction applied by the SH0ES team is wrong, it could bias the Hubble constant. The magnitude of the correction needed to resolve the tension, roughly 15 to 20% in the Hubble constant, would require a metallicity effect more than 3 times larger than the currently measured value. So, the metallicity hypothesis requires the Cepheid metallicity correction to be wrong by a factor of 3 or more. No evidence supports a systematic error of that size. The supernova sample itself has been scrutinized for selection effects, the possibility that the supernova used to measure the Hubble constant are not representative of the full population, either because of how they were selected for spectroscopic follow-up or because of host galaxy environment effects. Brighter supernovae tend to occur in younger stellar environments, and host galaxy mass correlates with supernova brightness at the percent level, a mass step that is corrected for in the analysis. Different analysis pipelines, using different statistical treatments of the mass step and different subsets of the supernova sample, give Hubble constants ranging from about 72 to 74. The spread reflects real uncertainty in the analysis. But none of the reasonable variations of the analysis brings the local value below 72, or close to 67.4. After the crowding corrections, the tension remained. The James Webb Space Telescope then provided the most direct test of crowding as an explanation. JWST observes in infrared wavelengths, where its diffraction-limited resolution, the fundamental limit set by the wave nature of light, is comparable to, or better, than the Hubble Space Telescope at optical wavelengths for nearby galaxies. But its superior sensitivity and stability allow it to measure Cepheids in these galaxies without the resolution limits that affect Hubble in more distant galaxies. The JWST measured Cepheids in 7 galaxies that anchor the supernova calibration, the same galaxies used by SHOEs, and found distances consistent with the Hubble Space Telescope measurements to within the statistical uncertainties. Crowding was not systematically biasing the SHOE's distances. Dust is another candidate. Interstellar dust absorbs and scatters starlight, making stars appear fainter and redder than they actually are. If dust in the Cepheid host galaxies is making the Cepheids appear fainter than their true brightness, the inferred distances would be overestimated, and the Hubble constant would be overestimated. The SH0ES team addresses dust by observing Cepheids in multiple optical and infrared bands. Because dust affects different wavelengths differently, it absorbs blue light more than red light, more red light than infrared. Measuring the color of a Cepheid tells you how much dust is in front of it. And the measurement in infrared wavelengths is much less sensitive to dust than optical measurements. The JWST infrared measurements again confirm the Hubble Space Telescope distances, arguing against dust as a systematic. Metallicity, the abundance of elements heavier than hydrogen and helium in the Cepheid host stars, affects the period luminosity relation at a level of a few percent per unit of metallicity difference. Cepheids in the calibration galaxies and Cepheids in the measurement galaxies have different typical metallicities, and if the metallicity correction applied by the SH0 team is wrong, it could bias the Hubble constant. The magnitude of the correction needed to resolve the tension, roughly 15 to 20% in the Hubble constant, would require a metallicity effect more than 3 times larger than the currently measured value. The metallicity hypothesis requires the Cepheid metallicity correction to be wrong by a factor of 3 or more. No evidence supports a systematic error of that size. The supernova sample itself has been scrutinized for selection effects. The possibility that the supernovae used to measure the Hubble constant are not representative of the full population, either because of how they were selected for spectroscopic follow-up or because of host galaxy environment effects. Brighter supernovae tend to occur in younger stellar environments, and host galaxy mass correlates with supernova brightness at the percent level, a mass step that is corrected for in the analysis. Different analysis pipelines, using different statistical treatments of the mass step and different subsets of the supernova sample, give Hubble constants ranging from about 72 to 74. The spread reflects real uncertainty in the analysis. But none of the reasonable variations of the analysis brings the local value below 72 or close to 67.4. What the James Webb Space Telescope did, definitively, was confirm that the Cepheid distances measured by the Hubble Space Telescope were not systematically biased by the instrument's limitations. This was the most direct test of the most scrutinized potential systematic in the distance ladder. The JWST result, published in 2023 and 2024, was unambiguous. The Hubble Space Telescope Cepheid distances were correct. The Hubble constant is 73, within the current measurement uncertainties. The systematic error hypothesis for the local measurement is essentially dead. The CMB side has its own systematic concerns. The Planck satellite operates at millimeter wavelengths, and separating the true CMB signal from the foreground emission of our own galaxy, from spinning dust grains, from synchrotron radiation of electrons spiraling in the galactic magnetic field, from free emission of ionized gas, requires sophisticated foreground models. The foreground subtraction is imperfect, and residual foreground contamination could bias the inferred CMB power spectrum and therefore the derived cosmological parameters. The Planck collaboration published an extensive series of papers specifically analyzing foreground systematics, concluding that the systematic uncertainties are subdominant to the statistical uncertainties in the parameter constraints. Independent CMB experiments, ACT, CPT, confirmed the Planck CMB power spectrum without the Planck foreground model, using different frequencies in different parts of the sky. They found consistent CMB power spectra and derived consistent cosmological parameters, including consistent Hubble constants around 67 to 68. Foreground contamination cannot explain the tension. At this point, the evidence strongly suggests that the Hubble tension is not caused by an error in any single measurement. And this is where the story becomes genuinely interesting, because something physical is causing it. Opens up a space of possibilities that ranges from a small modification to known physics to the standard model of cosmology is fundamentally wrong. No one knows yet which end of that spectrum the answer is on. What everyone agrees on is that the answer is not nothing. The universe is doing something. The current model does not predict, and the Hubble tension is the measurement that reveals it. Let's go through the proposed explanations, from the most conservative to the most radical, because the range of ideas that serious physicists have put on the table is itself a measure of how seriously the problem is being taken. The most conservative class of explanations involves modifying the late universe, adding or changing something about the universe after recombination, the epoch when the CMB was emitted. That would alter the expansion history between then and now without disturbing the early universe predictions. The CMB value of 67.4 is derived from early universe data combined with a model of how the universe evolved from then to now. If that model of evolution is wrong, if something changed in the late universe that the model doesn't account for, then the predicted current expansion rate would be wrong, and the discrepancy with the local measurement would be explained. One specific proposal in this category is a modification of dark energy. In the standard Lambda CDM model, dark energy is represented by the cosmological constant lambda, a fixed, unchanging energy density associated with empty space. It does not evolve. It does not change with time. Its value today is the same as its value a billion years ago. But dark energy could be dynamic. It could be a field that evolves over time, with an energy density that changes as the universe expands. A time-varying dark energy that was slightly different in the recent past from what the cosmological constant would predict could shift the expansion history enough to raise the predicted current Hubble constant from 67.4 towards 73. This is called quintessence, a dynamical dark energy model, and it has been studied for decades as an alternative to the cosmological constant. The problem with quintessence as an explanation for the Hubble tension is that most of the simplest models do not produce a large enough shift. You need a dark energy that was significantly different in the recent past, within the last few billion years, from what the cosmological constant predicts. And the perturbation needs to be in just the right direction and magnitude to resolve the tension without breaking anything else. The anything else constraint is important. The universe's expansion history is constrained not just by the CMB and the local distance ladder, but by baryon acoustic oscillations, a characteristic pattern in the large-scale distribution of galaxies whose scale serves as a standard ruler, and by weak gravitational lensing, the distortion of background galaxy images by intervening mass. Any modification to the expansion history must be consistent with all of these constraints simultaneously, not just the Hubble constant measurements. Fitting all constraints simultaneously while resolving the tension is harder than it sounds. More recent attention has shifted to modifications of the early universe, changes to what happened before or during recombination. These are more promising precisely because the CMB value is a prediction based on early universe physics. If something about the early universe is different from what Lambda CDM assumes, the prediction would be wrong, and the discrepancy could be explained without touching the local measurement at all. The most discussed early universe modification is called early dark energy. In this proposal, there was a brief period before recombination, around the time of matter-radiation equality, when the universe transitioned from being dominated by radiation to being dominated by matter, during which a dark energy component was temporarily important. This early dark energy would have added extra expansion before recombination, reducing the sound horizon, the distance that sound waves could travel in the early universe before recombination. The sound horizon is a crucial scale in cosmology. It is imprinted in the CMB power spectrum and in the baryon acoustic oscillation scale. If the sound horizon is smaller than lambda-CDM predicts, the inferred Hubble constant from CMB data is larger. Early dark energy makes the sound horizon smaller in a way that raises the predicted Hubble constant towards 73. The early dark energy model was proposed by Vivian Paulon and collaborators in 2018, and it attracted significant attention because it can, in principle, fully resolve the Hubble tension. The mechanism is physically motivated. Early dark energy can arise naturally in string theory and other extensions of the standard model of particle physics, and make specific predictions that can be tested against observations. The model predicts, for instance, a slight modification to the CMB power spectrum at specific angular scales, and it predicts a change in the matter power spectrum that affects how structures form and cluster. The problem is that the current data is not obviously consistent with early dark energy. When the full set of cosmological constraints, CMB, baryon acoustic oscillations, weak lensing, galaxy clustering, is analysed jointly, early dark energy models that resolve the Hubble tension tend to create tensions elsewhere. They resolve one discrepancy and introduce or worsen others. The Atacama Cosmology Telescope data, published in 2023, provides the most precise current constraints on early dark energy, and the results are not favourable. The data is consistent with no early dark energy at all. It does not rule out early dark energy at high confidence. The uncertainties are still large enough to allow some versions of the model, but it does not support it either. The next generation of CMB experiments, particularly the Simons Observatory, currently being built in Chile, and CMB S4, planned for the next decade, will have enough sensitivity to definitively confirm or rule out early dark energy. The answer is coming. Another early universe proposal involves extra radiation, additional species of relativistic particles present in the early universe beyond the 3 known flavors of neutrinos. The amount of radiation in the early universe is parameterized by something called N effective, or NEF, the effective number of relativistic species. The standard model predicts NEF of approximately 3.044, accounting for the 3 known neutrinos and their thermal properties. If NEF is slightly higher, if there was an additional species of light particle in the early universe, the expansion rate at recombination would have been higher, the sound horizon would have been smaller, and the inferred Hubble constant from CMB data would be larger. NEF of around 3.5 to 3.7, instead of 3.044, could in principle raise the CMB-derived Hubble constant to around 70, reducing the tension significantly. What could provide this extra radiation? A light, sterile neutrino, a 4th neutrino flavor that interacts only through gravity, not through the weak nuclear force. A light, dark sector particle that was in thermal equilibrium with the standard model plasma in the early universe, and then decoupled. An axion, a hypothetical particle, originally proposed to solve a problem in quantum chromodynamics that remained relativistic through recombination. Any of these could contribute to NEF in principle. The constraint from current data is that NEF is 2.99 plus 0.17, consistent with the standard model prediction, but with enough uncertainty to allow a modest increase. The Simons Observatory and CMBS-4 will measure NEF to a precision of about 0.03, which is tight enough to detect any physically interesting deviation from the standard model prediction. There is a different class of proposals that does not modify the early universe or the late universe, but instead questions the distance ladder itself, specifically the calibration of the first rung. The entire local measurement rests on the parallax-based distances to calibrator stars that anchor the Cepheid period luminosity relation. If those distances were wrong, if there was a systematic error in the parallax measurements, the whole ladder would be shifted. The most precise parallax measurements come from the Gaia satellite, the European Space Agency mission that has measured parallaxes to over 1 billion stars with micro-arcosecond precision. A subtle systematic error in Gaia's parallaxes, perhaps a scale error or a spatially varying bias, could shift the distance ladder calibration. This possibility was taken seriously enough that several groups have scrutinized the Gaia parallax data specifically for this kind of systematic. The conclusion is that Gaia's parallaxes may have a small systematic bias, the so-called Gaia parallax offset, at the level of a few micro-arcseconds. Corrections for this offset has been applied in the most recent SH0ES analyses. After applying the corrections, the tension remains at approximately 5 sigma. The Gaia parallax offset, real as it may be, is too small to explain the Hubble tension. Some researchers have proposed bypassing the Cepheid rung entirely. If Cepheids have some systematic issue that has not been identified, using a completely independent distance indicator that does not rely on Cepheids would either confirm or refute the local value. The main alternative is the tip of the red giant branch, or TRGB, a feature in the luminosity function of old red giant stars that occurs at a very specific absolute brightness. When a red giant star reaches the top of the red giant branch, it undergoes a helium flash, a sudden ignition of helium burning in its core, and its brightness drops sharply. The maximum brightness before this flash is called the TRGB, and it is nearly constant across different stellar populations, making it a reliable standard candle. The Carnegie-Chicago Hubble program, led by Wendy Friedman at the University of Chicago, has used TRGB distances rather than Cepheid distances to calibrate the distance ladder. Their results have been somewhat lower than SH0ES, around 69 to 70 km per second per megaparsec, which would reduce the tension with the CMB value from about 5 sigma to about 2 to 3 sigma. This is suggestive, but more recent analysis of TRGB distances, including work using the James Webb Space Telescope, have found that the TRGB calibration itself has systematic uncertainties related to the stellar population and metallicity of the calibrating stars. Different analysis of the same TRGB data give answers ranging from 69 to 72, depending on the assumptions made. The TRGB is not a clean resolution of the tension. Another distance indicator that has been applied to the Hubble constant problem is the surface brightness fluctuation method, a technique that measures the graininess in the surface brightness of elliptical galaxies to infer their distances. And water masers, clouds of water vapor orbiting the central black holes of certain galaxies, whose velocities can be measured precisely enough to give geometric distances via the same parallax principle used for nearby stars. but on an extragalactic scale. In gravitational time delays, the time difference between multiple images of a background quasar gravitationally lensed by a foreground galaxy, which depends on the absolute distance scale and gives a Hubble constant independent of the entire conventional distance ladder. The HARB-0-LICAO collaboration and its successor TDCO-SMO have used gravitational time delays from 6 lens quasars to measure the Hubble constant, getting approximately 73 kilometers per second per megaparsec, consistent with SMOES, not with Planck. The surface brightness fluctuation measurements give around 73 as well. The water maser measurement from the Megamaser Cosmology project gives 73.9, again consistent with the local distance ladder. Every method that measures the current expansion rate directly gives a value in the 70s. Every method that uses the early universe as a foundation gives a value around 67 to 68. The pattern is consistent and persistent. At this point, the evidence strongly suggests that the Hubble tension is not caused by an error in any single measurement. It is a genuine disagreement between the early and late universe that appears regardless of which specific technique is used. This is what elevates it from a calibration problem to a cosmological crisis. The universe at late times expands faster than the universe at early times, as predicted by lambda CDM would suggest. Something happened, or is happening, that is not in the model. What could that something be? One possibility that has gained significant traction recently is that dark energy is not the cosmological constant. In January 2024, the Dark Energy Spectroscopic Instrument, DESI, a spectrograph mounted on the 4-meter Mile telescope at Kitt Peak National Observatory in Arizona, equipped with 5,000 robotic fiber positioners that can simultaneously measure the spectra of 5,000 galaxies, published its first year of results from its Baryon Acoustic Oscillation Survey. The Sun, DESI. DESI measured the Baryon Acoustic Oscillation Scale across 14 different redshift bins, spanning from nearby galaxies to a look-back time of 11 billion years. The results showed a hint, not a detection, a hint that dark energy may have been evolving over cosmic time. Specifically, the data was slightly better fit by a dark energy model that was more negative than the cosmological constant in the past and is approaching the cosmological constant value today, a behavior that some models call phantom crossing. The statistical significance was about 2.5 to 3 sigma, not enough to claim a discovery, but enough to be taken seriously. DESI's Year 1 results were discussed in hundreds of papers within months of publication. The hint of evolving dark energy, if confirmed, would not directly resolve the Hubble tension. The specific behavior suggested by the data does not obviously push the predicted Hubble constant upward. But it would confirm that lambda CDM is not the final word on dark energy, which opens the door to modifications of the model that might resolve the tension. The Year 3 and Year 5 DESI data, expected over the next few years, will determine whether the hint is a real signal or a statistical fluctuation. If it persists and strengthens to 5 sigma, it will be the first direct evidence of evolving dark energy, a discovery on par with the original detection of the accelerating universe that gave Rius the Nobel Prize. Another distance indicator that has been applied to the Hubble constant problem is the surface brightness fluctuation method, a technique that measures the graininess in the surface brightness of elliptical galaxies to infer their distances. And water masers, clouds of water vapor orbiting the central black holes of certain galaxies, whose velocities can be measured precisely enough to give geometric distances via the same parallax principle used for nearby stars. But on an extragalactic scale. In gravitational time delays, the time difference between multiple images of a background quasar gravitationally lensed by a foreground galaxy, which depends on the absolute distance scale and gives a Hubble constant independent of the entire conventional distance lagger. The Hod-Zero-Lykow collaboration and its successor, TDCOSMO, have used gravitational time delays from 6 lensed quasars to measure the Hubble constant, getting approximately 73 kilometers per second per megaparsec, consistent with SCOES, not with Planck. The surface brightness fluctuation measurements give around 73 as well. The water maser measurement from the Megamaser Cosmology project gives 73.9, again consistent with the local distance ladder. Every method that measures the current expansion rate directly gives a value in the 70s. Every method that uses the early universe as a foundation gives a value around 67 to 68. The pattern is consistent and persistent. At this point, the evidence strongly suggests that the Hubble tension is not caused by an error in any single measurement. It is a genuine disagreement between the early and late universe that appears regardless of which specific technique is used. This is what elevates it from a calibration problem to a cosmological crisis. The universe at late times expands faster than the universe at early times, as predicted by lambda CDM would suggest. Something happened or is happening that is not in the model. What could that something be? One possibility that has gained significant traction recently is that dark energy is not the cosmological constant. In January 2024, the Dark Energy Spectroscopic Instrument, DESI, a spectrograph mounted on the 4-meter Mail telescope at Kitt Peak National Observatory in Arizona, equipped with 5,000 robotic fiber positioners that can simultaneously measure the spectra of 5,000 galaxies, published its first year of results from its Baryon Acoustic Oscillation Survey. DESI measured the Baryon Acoustic Oscillation Scale across 14 different redshift bins, spanning from nearby galaxies to a look-back time of 11 billion years. The results showed a hint, not a detection, a hint that dark energy may have been evolving over cosmic time. Specifically, the data was slightly better fit by a dark energy model that was more negative than the cosmological constant in the past and is approaching the cosmological constant value today, a behavior that some models call phantom crossing. The statistical significance was about 2.5 to 3 sigma, not enough to claim a discovery, but enough to be taken seriously. DESI's Year 1 results were discussed in hundreds of papers within months of publication. The hint of evolving dark energy, if confirmed, would not directly resolve the Hubble tension. The specific behavior suggested by the data does not obviously push the predicted Hubble constant upward. But it would confirm that lambda CDM is not the final word on dark energy, which opens the door to modifications of the model that might resolve the tension. The Year 3 and Year 5 DESI data, expected over the next few years, will determine whether the hint is a real signal or a statistical fluctuation. If it persists and strengthens to 5 sigma, It will be the first direct evidence of evolving dark energy, a discovery on par with the original detection of the accelerating universe that gave Rius the Nobel Prize. There are more radical proposals. Some physicists have suggested that the tension points to a modification of gravity itself. General relativity, the theory that underlies all of modern cosmology, has been tested with extraordinary precision within the solar system and in the regime of strong gravity near neutron stars and black holes. On cosmological scales, it has been tested through the CMB, through galaxy clustering, through gravitational lensing. All of these tests are consistent with general relativity. But the tests are not infinitely precise, and there is room, within the current uncertainties, for small modifications. Modified gravity theories that add terms to the Einstein equations that become significant on very large scales or at very low densities, have been proposed as possible explanations for dark energy. Some of these theories have implications for the Hubble constant that could resolve the tension. The problem with modified gravity as a resolution of the Hubble tension is the same problem that plagues most proposed solutions. It is very hard to modify one thing without breaking something else. The baryon acoustic oscillation scale, the CMB power spectrum, the growth rate of large-scale structure, the lensing signal from galaxy clusters, all of these constrain the expansion history and the growth of structure in ways that are tightly coupled. A modified gravity theory that raises the Hubble constant tends to modify the growth of structure in a way that produces tensions with galaxy clustering measurements. The space of modifications that resolve the Hubble tension without creating new tensions elsewhere is very small. Some physicists have proposed something more drastic, that the tension is telling us the universe is not homogeneous and isotropic on the scales we assume it is. The standard model of cosmology rests on the cosmological principle, the assumption that the universe is the same in every direction and at every location, on sufficiently large scales. This principle is supported by the extraordinary uniformity of the SMB, a uniformity that varies by only 1 part in 100,000, and by the statistical homogeneity of galaxy surveys on scales larger than a few hundred megaparsecs. But what if the local universe, the region within a few billion light-years from which the local Hubble constant measurement is made, is not representative? What if we happen to live in an underdense region, a cosmic void, that is expanding slightly faster than the global average? A large underdense region, a local void, could cause local measurements of the Hubble constant to overestimate the global value, because the accelerated expansion inside the void would add to the apparent recession velocities of nearby galaxies. The size of the void needed to explain the full 5 km per second per megaparsec discrepancy is substantial, hundreds of megaparsecs in radius, and surveys of the large-scale structure around us do find some evidence for a local underdensity, sometimes called the KBC void, after the researchers who characterized it in 2013. Whether this underdensity is large enough and deep enough to explain the full Hubble tension is debated. Recent analysis suggests it might explain part of the tension, perhaps 1 to 2 kilometers per second per megaparsec, but not all of it. There is another class of explanation that sits at the intersection of cosmology and particle physics, modifications to the nature of dark matter. Cold dark matter, a CDM. In lambda CDM is assumed to consist of particles that were non-relativistic at the time of matter radiation equality and that interact only through gravity. But what if dark matter has additional interactions with itself, or with dark energy, or with standard model particles that affect the expansion history in subtle ways? Interacting dark matter models can produce changes in the sound horizon and in the growth of structure that might resolve the Hubble tension, or potentially also explain other small tensions in the cosmological data, such as the S8 tension, the discrepancy between the predicted and measured amplitude of matter fluctuations on large scales. The S8 tension is worth mentioning here because it may be related to the Hubble tension. S8 is a parameter that combines the matter density and the amplitude of density fluctuations, and it has been measured both from the CMB, which predicts a value from early universe data, and lambda CDM, and from weak gravitational lensing surveys, which measure the matter fluctuations directly. The CMB-based prediction and the lensing measurements disagree at a level of about 2 to 3 sigma, less severe than the Hubble tension, but in a similar spirit. Early universe predictions and late universe measurements don't quite agree. If both tensions have the same root cause, if there is a single modification to lambda CDM that resolves both the Hubble tension and the S8 tension simultaneously, that would be a strong argument for the modification. So far, no proposed modification does both cleanly. The gravitational wave approach to measuring the Hubble constant deserves specific attention because it is entirely independent of both the CMB and the conventional distance ladder, and it will become increasingly powerful over the next decade. When two neutron stars or two black holes merge, they produce gravitational waves, ripples in the fabric of space-time, whose amplitude encodes the absolute distance to the merger. No calibration chain is needed. No parallax, no Cepheids, no supernovae. The gravitational wave signal itself carries the distance information because the amplitude of the wave falls off with distance in a precisely calculable way. Measuring the amplitude of the wave gives the distance. Measuring the recession velocity of the host galaxy from its electromagnetic spectrum gives the velocity. The ratio gives the Hubble constant. This is called the standard siren method, by analogy with standard candles, which use brightness to measure distance. The first standard siren measurement came from the neutron star merger GW170817, detected on August 17, 2017 by LIGO and Virgo. The merger was localized to the galaxy NGC 4993, whose recession velocity was known. The gravitational wave distance measurement gave a Hubble constant of 70, with an uncertainty of about 12 kilometers per second per megaparsec, too uncertain to resolve the tension, but right in the middle of the two measurements, which was noted with interest. As LIGO and Virgo collect more neutron star merger events, the current rate is a few per year, the statistical uncertainty on the gravitational wave Hubble constant measurement will decrease. After about 50 events, the uncertainty should shrink to a few percent, enough to definitively favour one of the two competing measurements. After a few hundred events, the measurement will be as precise as the current CMB or distance ladder measurements. The upgraded LIGO detectors, currently operating in their fourth observing run 04, are detecting compact binary mergers at a higher rate than the previous run. The next generation of gravitational wave detectors, the Einstein Telescope in Europe and Cosmic Explorer in the United States, both currently in planning and early development, will be sensitive enough to detect neutron star mergers throughout the observable universe, accumulating thousands of events per year. These instruments will produce Hubble constant measurements with sub-percent precision, entirely independent of both the CMB and the distance ladder. When they come online, in the 2030s or 2040s, the Hubble tension will either be confirmed or resolved by gravitational waves alone. The Vera Rubin Observatory, officially the Legacy Survey of Space and Time, or LSST, currently undergoing commissioning in Chile as of 2025, will contribute to the Hubble tension problem through multiple channels. It will discover tens of thousands of Type 8 supernovae per year, vastly expanding the supernova sample used for the local Hubble constant measurement. It will measure weak gravitational lensing across enormous areas of sky, tightening the S8 constraint. It will discover thousands of strongly lensed quasars, expanding the TD-Cosmo time delay cosmography sample from a handful to potentially hundreds of systems. The statistical power of the Rubin data will be large enough to either confirm the tension at extremely high significance or reveal systematics in existing measurements at a level of precision current data cannot achieve. There are 2 upcoming space missions specifically designed to address the dark energy and Hubble constant questions. The Euclid satellite, launched in July 2023 by the European Space Agency, is currently conducting a wide-field imaging and spectroscopic survey of the galaxy distribution. Over its 6-year mission, Euclid will map the 3-dimensional positions of hundreds of millions of galaxies, measuring baryon acoustic oscillations and weak lensing across the full sky. The Nancy Grace Roman Space Telescope, NASA's next large space observatory after JWST, will conduct a high-latitude wide-area survey that will complement Euclid's coverage and add supernova cosmology measurements. Both missions are designed to measure the equation of state of dark energy, whether it is truly constant, as the cosmological constant requires, or whether it evolves. The DESI hint of evolving dark energy makes the Euclid and Roman results even more consequential. What should you actually believe, given all of this? The honest answer is that nobody knows what is causing the Hubble tension. The measurements are real, the tension is real, the proposed explanations range from plausible but incomplete to speculative. No single model cleanly resolves the tension without creating problems elsewhere. The field is genuinely in a state of active controversy, not the kind of staged controversy that journalists manufacture to create drama, but the real kind, where smart people have looked at the same data and reached different conclusions about what it means. What the evidence does support is a clear ranking of possibilities. Systematic errors in the measurements, once the most popular explanation, are increasingly untenable. The Webb telescope confirmation of Cepheid distances was the most recent and most powerful argument against the systematic error hypothesis. The internal consistency of all local measurements around 73 and all early universe measurements around 67.4 further argues against a single systematic error explaining the whole tension. The problem is real. Among the physical explanations, early dark energy and extensions of the neutrino sector are the most actively pursued and the most testable in the near term. Early dark energy has the advantage of being able to fully resolve the tension and being theoretically motivated. It has the disadvantage of currently being in mild tension with the ACT-CNB data. The Simons Observatory, beginning observations in 2024, will produce a definitive test within a few years. Modifications to dark matter and dark energy are more speculative, but cannot be ruled out with current data. The gravitational wave measurement is the most model-independent future probe. It uses physics that is not connected to either the CMB analysis pipeline or the distance ladder calibration chain. If the gravitational wave Hubble constant, as it accumulates precision over the coming decade, converges on 73, that strongly favours the local measurements and argues that something is wrong with the lambda CDM prediction from the CMB. If it converges on 67.4, that is a serious challenge to the distance ladder and suggests that systematic errors not yet identified are responsible. If it comes in between, at 70, say, that raises the possibility that both the CMB and the local measurements have small, systematic errors pushing them in opposite directions, and the true value is in the middle. The resolution of the Hubble tension, when it comes, will be one of the most significant moments in modern cosmology. If it turns out to be a systematic error, the resolution will be a lesson in measurement precision and the difficulty of controlling biases in complex observational chains. If it turns out to be new physics, early dark energy, extra-relativistic species, modifications to gravity, evolving dark matter, the resolution will open a new chapter in our understanding of the universe. It may require adding a new parameter to lambda CDM, as happened when the accelerating expansion was discovered and the cosmological constant was added. It may require replacing lambda CDM with a fundamentally different framework. What it will not be is nothing. The Hubble tension is too large, too persistent, too consistently reproduced by too many different methods to dissolve quietly. Something is out there in the difference between 67.4 and 73, something the universe is trying to tell us. We have not yet learned to read the message. The instruments being built right now, DAISY, Euclid, Roman, Rubin, Simon's Observatory, Advanced LIGO, eventually the Einstein telescope, are the tools with which that message will be decoded. The universe has been expanding since the Big Bang, 13.8 billion years ago. It will continue expanding for longer than any human mind can comfortably contemplate. Trillions of years. Until the last stars go dark, and the last black holes evaporate, and the last structures dissolve in the increasing emptiness of a cosmos that has run out of things to do. We have been studying it for about a century, with modern instruments. We have learned an extraordinary amount. We have built a model that works with remarkable precision across an enormous range of scales and epochs. And the universe, and the number 73 versus 67.4, is telling us the model is not complete. Not wrong in the way that a fundamentally flawed theory is wrong. Lambda CDM is far too successful for that. But incomplete in the way that Newton's mechanics was incomplete before Einstein. Correct in most regimes, breaking down at the edges, pointing towards something deeper that we have not yet found. Two numbers. A gap of 5.6 kilometers per second per megaparsec. A 10% discrepancy in the most fundamental parameter describing the universe's current state. Confirmed by a dozen independent methods. Unexplained by any model that does not break something else. This is what a genuine scientific frontier looks like. Not a mystery invented for drama, not a problem without data. A real discrepancy, precisely measured, honestly reported, and actively being hunted by every major astronomical instrument, on Earth and in space. The answer is coming. We do not yet know what it will be. That is exactly how real science works. But before we get to the instruments that will deliver the answer, we need to spend more time on the alternative distance indicators, the rungs of the ladder that are not Cepheids, because they tell a story that is important for understanding where the tension actually lives. Number 2, what is? The tip of the red giant branch, or TRGB, is the most developed alternative to Cepheids as a distance indicator. Red giant stars are stars that have exhausted the hydrogen in their cores and expanded dramatically, burning hydrogen in a shell around the core. As the core grows denser and hotter under the weight of the overlying material, the star climbs the red giant branch in the Hertzsprung-Russell diagram, getting brighter but not much hotter. When the core temperature reaches about 100 million Kelvin, helium ignites in a flash, the helium flash, and the star rapidly reorganizes into a horizontal branch configuration. The maximum brightness reached just before the helium flash is the TRGB. Because the helium flash is triggered at a specific core temperature set by quantum mechanics and nuclear physics, the TRGB luminosity is nearly constant across different stellar populations. In the infrared I band, the TRGB has an absolute magnitude of approximately -4.05, consistent to a few percent across populations spanning a range of ages and metallicities. Wendy Friedman's Carnegie-Chicago Hubble program measured TRGB distances to 18 galaxies and calibrated the supernova distance ladder using those distances. Publishing results in 2019 and 2021 that gave Hubble constants around 69.6 to 69.8. These values sit between the CMB measurement of 67.4 and the SH0 ECP'd measurement of 73.04. Friedman interpreted the result as evidence that the Hubble tension might be partly a systematic error in the CP'd distances, that CP'ds and TRGB give different calibrations of the supernova distance scale, and that the truth lies somewhere between the two. The James Webb Space Telescope provided a critical test. JWST observed both Cepheids and TRGB stars in the galaxy NG4258, a galaxy with a precise geometric distance from water masers orbiting its central black hole, which anchors the entire distance scale independently of parallax. The JWST measurements confirmed the Cepheid distances measured by Hubble. They also found that the TRGB distance to NGB 4258 from JWST was consistent with the maser distance, but that the calibration of the TRGB method itself has systematic uncertainties that depend on how the tip is identified in the luminosity function. Different analysis choices, different smoothing kernels, different color cuts, different treatment of the stellar population give TRGB distances that differ by a few percent, which translates into differences in the Hubble constant of a few kilometers per second per megaparsec. The 2024 analysis by Friedman and collaborators, using JWST data on the TRGB in multiple galaxies, gave a Hubble constant of 69.96, still between the CMB and SH0 ES values, but closer to the CMB. A competing analysis by Skolnick and collaborators, using the same JWST data but different TRGB calibration choices, gave 72.05. The TRGB is not resolving the tension. It is revealing how sensitive distance measurements are to analysis choices at the percent level. Water masers provide the most geometrically Doric extragalactic distance measurement available. In certain galaxies with active galactic nuclei, galaxies with supermassive black holes accreting material, the accretion disk around the black hole is edge-on to our line of sight, and water molecules in the disk mace. They produce stimulated emission of radio waves at 22 GHz, the same transition used in microwave ovens. The maser spots trace the disk at known positions and with known velocities. By measuring the positions, velocities and accelerations of the maser spots over years of monitoring, you can determine the angular diameter of the disk, the physical size of the disk, from Keplerian dynamics, and from those two quantities, the distance the same parallax principle that works for nearby stars, extended to megaparsec scales through pure geometry. The Mega Mesa Cosmology Project monitored water mesas in 6 galaxies over more than a decade, measuring distances to each with geometric precision. The resulting Hubble constant from 6 independent galaxy distances is 73.9 plus or minus 3.0 kilometers per second per megaparsec, consistent with SH0e, inconsistent with Planck. The Mesa method has larger uncertainties than Cepheids or supernovae because the number of suitable Mesa galaxies is small. Finding an active galactic nucleus with an edge-on accretion disk that produces strong Mesa emission is rare. But those large uncertainties come from small sample size, not from calibration uncertainty. Each individual Mesa distance has a well-understood geometric error budget with no calibration chain. The Mesa method is arguably the most trustworthy local distance measurement available, and it agrees with SH0ES. Gravitational time delays deserve extended treatment because they are entirely independent of any stellar distance indicator. When a massive galaxy lies between us and a more distant quasar, a luminous active galactic nucleus billions of light years away, the galaxy's gravity bends the quasar's light into multiple images, each following a different path through the curved space-time around the lensing galaxy. Because the paths have different lengths and pass through regions of different gravitational potential, the travel times are different. If the quasar's luminosity varies, as quasar luminosities often do, on timescales of days to weeks, the variability pattern appears in each image at different times. The time delay between images is measured directly by monitoring the images over years. The time delay depends on the absolute distance scale, specifically on a combination of the distances from us to the lens, from us to the quasar, and from the lens to the quasar. With a model for the mass distribution of the lensing galaxy, the time delay gives the Hubble constant. The HAL-0-LICAO collaboration measured time delays in 6 strongly lensed quasar systems and published a joint Hubble constant of 73.3 plus or minus 1.8 in 2020. Their successor collaboration, TDCOS-MOSA, reanalyzed the same data with more flexible mass models for the lensing galaxies and found 74.2 plus or minus 1.6, still consistent with SH0ES, still inconsistent with Planck. A subsequent TDCOS-MO analysis that combined the time delay data with kinematics of the lensing galaxies to constrain the mass models from 2 directions simultaneously gave 67.4 plus or minus 4.1, suddenly consistent with Planck, though with large uncertainties. The lensing community spent considerable time debating which analysis was correct. The conclusion was that the mass model uncertainty, specifically the mass sheet degeneracy, a mathematical degeneracy that allows a range of mass distributions to produce the same image configuration, was not fully broken by the original H0-LICAO analysis. The TDCOS-MO result with kinematics is more conservative and more reliable, but it has larger uncertainties that prevent it from discriminating between the 2 competing H-Hubble constant values. The Rubin Observatory Time Delay Cosmography program, which will find thousands of strongly lensed quasars in the LSST survey, will break the mass sheet degeneracy statistically by analyzing large numbers of lenses simultaneously. With hundreds of lensed quasar systems, the statistical power will be enough to constrain the Hubble constant to better than 1% from time delays alone, with the mass model uncertainty controlled by the ensemble of lensing galaxy kinematics. This measurement, expected in the late 2020s and early 2030s, will be a definitive test of the Hubble tension from a completely independent method. Surface brightness fluctuations, SBF, work on the principle that a nearby galaxy, when imaged at high resolution, appears grainier than a distant galaxy of the same apparent size. A nearby galaxy subtends a larger solid angle on the sky, so each pixel in the image contains fewer stars. The statistical fluctuation in the number of stars per pixel is larger for a nearby galaxy than a distant one. The amplitude of these fluctuations, calibrated against a known distance indicator, gives the distance to the galaxy. CBF is most reliable for elliptical galaxies and for the bulges of spiral galaxies, where the stellar population is old and well characterized. The CBF distance indicator was calibrated against Cepheid distances in the original work by Tomry and Schneider in the 1980s, and has been recalibrated against JWST measurements more recently. John Blakesley and collaborators used SBF distances to 63 early type galaxies to measure a Hubble constant of 73.3 plus or minus 2.5 in 2021. The SBF method is independent of Cepheids, independent of supernovae, independent of lensing. It uses a completely different physical phenomenon, and it gives 73. Carnell and collaborators, using a different SBF calibration, gave 73.7 plus or minus 2.6 in 2024. Every local method that uses actual distance measurements to galaxies in the regime where the Hubble flow dominates gives a value in the range 72 to 75. The pattern is unbroken. This systematic agreement of all local methods with each other and systematic disagreement of all local methods with all early universe methods is the core of the crisis. It is not that one measurement disagrees with another. It is that a class of measurements, everything that directly probes the expansion rate today, disagrees with a different class of measurements, everything that probes the expansion rate through the filter of a cosmological model applied to early universe data. The dividing line is not between different teams, or different telescopes, or different analysis choices. It is between measuring today and predicting today from the past. Something changed between the early universe and now. Or, the model of how the early universe maps to the present is wrong. Those are the same statement, written two different ways. The honest assessment of where the field stands in 2025 is this. The Hubble tension is real. It is at the 4 to 5 sigma level. It has survived every systematic check that has been thrown at it, and no proposed physical explanation has been confirmed. Several explanations, early dark energy, extra-relativistic species, interacting dark matter, modified gravity, remain viable, but each faces constraints from data that limit how completely they can resolve the tension without creating problems elsewhere. The DESI hint of evolving dark energy, if confirmed by future data, will not resolve the tension directly, but will confirm that the cosmological constant is not the final description of dark energy, opening theoretical space for models that might. The next 5 years will be decisive. The Simons Observatory will test early dark energy. DESI Year 3 and 5 will characterize the dark energy equation of state. The Vera Rubin Observatory will accumulate tens of thousands of Type Ia supernovae, tightening the local Hubble constant measurement and checking for systematics in the supernova sample at a level impossible with current data. Euclid will measure baryon acoustic oscillations and weak lensing across the sky. Advanced LIGO will accumulate gravitational wave standard sirens. Each of these datasets will add independent constraints that either support or challenge the proposed solutions. If early dark energy is confirmed by Sinon's observatory, the resolution of the Hubble tension will require modifying lambda CDM by adding a new component to the early universe, a field that was briefly important around matter radiation equality and then decayed away. The modification would be similar in spirit to the addition of inflation to explain the CMB uniformity, a new physical ingredient, theoretically motivated, but not yet directly observed, required to make the model consistent with all observations. If early dark energy is ruled out by Simon's observatory and the gravitational wave standard sirens converge on Centi 3, the resolution becomes harder. No early universe modification is ruled out. No late universe modification is ruled out. But the most discussed candidate is eliminated. The field would need new ideas. This is where the radical proposals, modifications of gravity, violations of the cosmological principle, new dark matter interactions would receive more serious attention. If the gravitational wave standard sirens converge on 67.4, the local distance ladder has an unidentified systematic at the few percent level. This would be the most astonishing outcome, not because it would require new physics, but because it would require that a decade of systematic error hunting by multiple independent teams using multiple independent distance indicators all missed the same bias. Possible, but the least likely of the three scenarios, given the current evidence. The universe is 13.8 billion years old. Human beings have been measuring its expansion rate with modern instruments for less than a century. We have built a model, lambda CDM, that works with extraordinary precision across an enormous range of observations, and we have found a crack in that model at the level of 10% in one parameter. The crack has been there for a decade, getting sharper with each new measurement, resisting every attempt to explain it away. It is telling us something. We do not yet know what. 73 versus 67.4. Before we close, it is worth being explicit about what is actually at stake. If the Hubble tension turns out to require genuinely new physics, because the phrase new physics gets used loosely and its implications are not always spelled out. Lambda CDM is not just a description of the universe. It is a synthesis of three separate frameworks: general relativity, which describes the geometry and dynamics of space-time; the standard model of particle physics, which describes the fundamental constituents of matter and their interactions; and a set of initial conditions set by cosmic inflation, which explains why the universe looks the way it does at early times. Lambda CDM is the cosmological application of all three frameworks simultaneously. When it works, and it works extraordinarily well, it works because all three frameworks are approximately correct, and because the initial conditions produced by inflation are consistent with what we observe. If the Hubble tension requires new physics, the new physics has to fit into this synthesis. Early dark energy, for example, is a modification at the interface of general relativity and particle physics, a new scalar field that couples to gravity and to the energy content of the universe in the early epoch. It fits naturally into both frameworks. Scalar fields are common in extensions of the standard model, and their gravitational effects are straightforwardly incorporated into general relativity through the Einstein equations. Adding early dark energy to lambda CDM does not break the existing frameworks, it extends them. Modified gravity is more radical. It changes the rules of general relativity itself, the equations governing how space-time curves in response to energy and matter. General relativity has been tested on solar system scales and in the strong field region near neutron stars and black holes with extraordinary precision. Modifying it on cosmological scales requires the modification to be invisible at shorter scales. It must reduce to general relativity in the regimes where general relativity has been tested. This is a serious constraint. Most modifications of gravity that produce interesting cosmological effects are already ruled out by solar system tests or gravitational wave observations. The space of viable modifications is narrow. Modifications to the nature of dark matter are at the interface of particle physics and cosmology. Called dark matter, massive particles interacting only through gravity is well tested through the CMB power spectrum, through the galaxy power spectrum, through the abundance of galaxy clusters. Adding interactions to dark matter changes all of these predictions. The interactions must be small enough not to ruin what lambda CDM already predicts correctly, but large enough to resolve the Hubble tension. This is a tight target. The most striking aspect of the Hubble tension, from a theoretical perspective, is not that it requires new physics. Many physicists expected that lambda CDM would break down at some level, but that the required new physics has to operate at a very specific place in the history of the universe. The discrepancy is between early universe predictions and late universe measurements. Something changed, or something was present in one epoch and not the other. If the answer is early dark energy, it was important briefly around matter radiation equality, and then irrelevant. If the answer is extra-relativistic species, they were present in the radiation-dominated era, and then became non-relativistic. If the answer is a local void, it is a feature of the very recent universe. Whatever the resolution is, it is not a uniform modification to all epochs equally. It is localized in cosmic time. This localization in cosmic time is a powerful constraint. It means the new physics has to know, in some sense, when to be important and when to turn off. For a scalar field like early dark energy, this is natural. Fields roll down their potential energy landscapes, being important when the potential energy dominates kinetic energy and becoming irrelevant as they roll to the minimum. For modified gravity, it is harder. You need the modification to be important at some scale or energy and negligible at others. For extra-relativistic species, it is automatic. Particles are relativistic when the temperature is high compared to their mass, and non-relativistic when the temperature drops below their mass. The Hubble tension, in this sense, is not just a number, it is a pointer. It is pointing to a specific place in cosmic history and saying something happened here that the model does not account for. Whether the something is a new particle, a new field, a modification of gravity, or a feature of our local environment, the tension is telling us where to look and what scale the new physics operates at. The instruments of the next decade will follow that pointer and find what it points to. Not by a little, not by a rounding error. By an amount that, if it is real and not a systematic, requires either new physics in the early universe, new physics in the late universe, or a fundamental modification to the framework within which we have been interpreting cosmological observations for 30 years. Each of those options, if confirmed, would be a discovery comparable in importance to the original measurement of the accelerating expansion, or the detection of the cosmic microwave background, or the confirmation of Big Bang nucleosynthesis. Each would open a chapter of cosmology that does not yet exist. Two numbers, one doubt. The most important, unresolved problem in modern cosmology, measured to 5 decimal places, confirmed by a dozen independent methods, unexplained by any model that does not break something else. The answer is in the data being collected right now by instruments on mountaintops and in orbit, accumulating photons and gravitational waves and galaxy spectra, piece by piece, toward a resolution that will change how we understand the universe we live in.